convection heat transfer. This heat transfer always takes place in the presence of a fluid which is moving on a solid surface. There are various mechanisms involved at the level of fluid. The important are advection, which is physical transport of the fluid, then diffusion, it is a conduction in the fluid, and the generation, it is heat generation due to fluid friction due to viscous forces. Now, mechanism of convection. Convection heat transfer is complicated because in this heat transfer, both fluid motion and heat conduction involves. This fluid motion enhances heat transfer, and for calculating the rate of convection heat transfer, we use Newton's law of cooling, which is HA Ts minus T infinity if you want in watts, and if you want watt per meter square, then it is H Ts minus T infinity, where Ts is the temperature of the surface and T infinity is the temperature of the ambient environment. In convective heat transfer, the H, which is called as convective heat transfer, can be defined as follows. Clearly we can see the layer which is in direct contact with the surface is at no slip condition, that is, it is at rest, and because of this the heat transfer only takes place by conduction through the fluid. Therefore, this H is defined as shown below. This H is a fluid property and it depends on the roughness of the solid surface and the type of the fluid flow. Now, convection. Type of convection. Convection may be of two types. Free or natural convection, in which the fluid flow is induced by buoyancy forces, and second one is forced convection, which is in which the motion of the fluid is driven by some fan, blower or compressor. In both type of convection, that is free convection and forced convection, phase changes may occur or may not. Okay, the typical values of H are given. We can clearly see that in case of boiling and condensation, the values of convective heat transfer is very high. Now, the very important phenomena for the convection is the boundary layer phenomena. What happens in the boundary layer phenomena, as we all know, that the fluid is flowing over the surface, say a hot surface or cool surface, and because of that, the layers which are in direct contact with the surface are at rest. This condition is called, or this assumption is called, no slip condition. And as we move in the upward direction, then the velocity increases slowly. That depends on the type of flow, and ultimately the fluid velocity becomes u or v infinity and temperature becomes T infinity. So this all happens in the very small region near the surface, which is called as boundary layer. Now, as a result, the heat transfer from the solid surface to the fluid layer adjacent to the surface by pure conduction. As we know, the fluid is at rest. This H in general varies along the flow direction. It is in the flow direction, not in the upward direction. The mean or average coefficient, convection heat transfer coefficient, can be determined by averaging the local heat transfer coefficient over the entire surface. Now again we come to the boundary layer concept. As shown in the figure, the u infinity is the free stream velocity of the fluid, and as it moves over the surface, due to no slip condition, boundary layer creates, or we can say that there is a velocity gradient in the very small region near the surface. Similarly, due to change in velocity, temperature also varies in this region, and there is a temperature field. For calculating the values of H, what we do, we have to determine the values of U and T, that is flow field and temperature field in the boundary layer region. Now, as we have discussed that there are two regions, flow field and the temperature field, then first of all we should discuss the flow field, that is how the velocity is changing near the surface. We can easily see at x equal to 0, that is at the starting, the velocity of the fluid is u infinity, and as we move in the x direction, we can see the boundary layer is getting developed. Initially in the laminar region, when the flow is smooth and streamlined, its thickness is very small, and as we are moving towards the x direction, the flow becomes turbulent, and in turbulent flow, the flow becomes chaotic. That is moment transfer between the layers. In between these two, there is a transition region in which the flow becomes turbulent from the laminar. Okay. Now, we should know about the velocity profile in different types of flows. In laminar region, most of the time the velocity distribution is parabolic, but in case of turbulent flow, it becomes flatter. For understanding turbulent region, we have to understand the laminar sublayer. The fluid layers which are in the immediate vicinity of the surface in the turbulent region, these are laminar sublayers. At these places, viscous effects are dominant. Thereafter, both laminar and turbulent effect exist. This is called buffer layer, and finally it is turbulent layer. Now, characteristics of convection. As we all know, this convection is extremely diverse, and several parameters are involved in this, like fluid properties, geometry of the flow, nature of the flow, phases. Therefore, to solve it, a systematic approach required. That is to depends on the understanding the physics behind each phenomena. We have to first identifying the parameter governing the flow, and then we group them into a meaningful non-dimensional numbers, which are called non-dimensional numbers, non-dimensional parameters. Then how to solve a convection problem? As we all know that most of the phenomena are governed by the fundamental laws of physics, that is conservation of mass, conservation of momentum, and conservation of energy. In case of conduction, we have to consider only conservation of energy. We are not bothered about the convection of mass and conservation of momentum, as there is no bulk motion. But in case of convection, we have to consider all the governing equations, that is conservation of mass, momentum, and energy. And after getting this governing equation, using boundary condition, we can solve the convection problem. But since this phenomena is complex, therefore what we do, we group the large numbers of parameters in some non-dimensional parameters, which are as follows. First is Nusselt number. It is a very important non-dimensional parameter in case of convection. It is nothing but it is it represents the enhancement of heat transfer through a fluid as a result of convection relative to conduction across the same boundary layer. Means if the heat transfer by convection is more, if it is dominant than the heat transfer by conduction, then we say that Nusselt number is high. Then comes Reynolds number. In case of flow, the very important part is viscous forces, and the ratio of inertia forces and viscous forces is called as Reynolds number. And at large Reynolds number, the inertia forces, which are proportional to the density and velocity of the fluid, are large due to the viscous forces. Thus, the viscous forces cannot prevent the random and rapid fluctuation of the fluid. The Reynolds number value is different for different types of flow. Say, consider the example of external flow, that is flow over a flat plate. The critical Reynolds number is 5 into 10 raised to power 5, means below this the flow is laminar and above this the flow is turbulent. If we consider the internal flow, that is flow through smooth pipes, then the Reynolds number is less than 2000 for laminar flow, greater than 4000 for the turbulent flow, and in between the flow is transitional. Now Prandtl number, it is the ratio of molecular diffusivity of momentum to the molecular diffusivity of heat. Means it is a measure of relative thickness of the velocity and thermal boundary layer, where fluid properties are mass density, as we all know, rho, dynamic viscosity is mu, thermal conductivity is K, specific capacity is Cp, kinematic viscosity is nu, and thermal diffusion is alpha. Now, after considering that thermal boundary layer, or say hydrodynamic boundary layer, the thermal boundary layer is another phenomena which is very important in the study of convection heat transfer. Similar to velocity boundary layer, turbulent boundary layer develops when a fluid at a specific temperature flows over a surface which is at different temperature. The thickness of the thermal boundary layer is defined as the distance at which this T minus Ts upon T infinity minus Ts becomes 99% of the original velocity. The relative thickness of the VBL and the TBL is described by the Prandtl number. As shown in the figure, effect of Prandtl number is shown. When the effect Prandtl number is more than 1, we can easily see that the thermal boundary layer lies within the hydrodynamic boundary layer. It happens in the case of oil. Similarly, in case of air and gases, the Prandtl number is 1. It means both of the thermal boundary layer and hydrodynamic boundary layer thickness are same. But in case of liquid metals, the hydrodynamic boundary layer is contained within the thermal boundary layer. In this case, Prandtl number becomes 1. As shown in this slide, for low pressure fluid, lipid metals, heat diffuses much faster than the momentum flow, and the velocity boundary layer is fully contained within the TBL. On the other hand, for high